Hi, I'm Adam. This is the Machine Tech video blog, and today I'm anodizing aluminum for an air bearing. In the last video, I machined the aluminum body and graphite insert for a flat aerostatic bearing. If you haven't watched that video yet, you should do it. If you have watched that video, it's time to anodize the aluminum body. Yay! Anodizing is, in effect, controlled corrosion of aluminum. Most metals react readily with oxygen to form oxides, but aluminum is especially reactive. A piece of aluminum exposed to oxygen in the atmosphere will form a layer of aluminum oxide on its surface within a tiny fraction of a second, albeit only a few nanometers thick. This reaction is a type of corrosion similar to the process which forms rust or iron oxide. You might ask, why doesn't aluminum disintegrate like iron or steel when exposed to the elements? Well, unlike rust, which is crumbly and quickly flakes off and exposes more iron underneath, the thin aluminum oxide layer actually prevents further oxidation of the underlying aluminum. Anodizing amplifies and accelerates this natural oxidation process by dunking the aluminum in an electrolyte solution and passing an electrical current through it. There are many benefits to anodizing. The two biggest ones are, 1. Improved wear resistance, and 2. Colorability. First, aluminum oxide is one of the hardest substances known. It's the same stuff used in most abrasive grinding wheels. So it makes sense that the oxide surface layer produced by anodizing improves the wear resistance of an aluminum part. Second, a very close microscopic examination of the anodized aluminum surface will reveal that its outer layer is not uniformly smooth, but rather covered in a grid of extremely fine pores. These pores can retain dye, providing near endless possibilities for decorative appearances. Just a quick point. Another, let's say, side effect of anodizing is that it provides electrical insulation. That's because, while aluminum is a very good conductor of electricity, aluminum oxide is a very poor conductor of electricity. Depending on the application, this may or may not be desirable for the finished part, and as you'll see later, the insulating property of aluminum oxide will affect material selection and power consumption during the anodizing process. There are 3 main types of anodizing recognized by military specification MIL A8625, the most cited standard for anodic coatings on aluminum. The 3 types are differentiated by the active agent in the anodizing solution and the specific parameters of the anodizing process. Type 1 is the oldest form of aluminum anodizing. The active agent is chromic acid. The oxide layer is thin, about 50 millionths of an inch, and has a low porosity. It's used to increase corrosion resistance, but it has a negligible effect on wear resistance, and it's not very well suited to coloring. Type 2 is by far and away the most common process. The active agent is sulfuric acid. The oxide layer is thicker, about 0.5 of a thousandth of an inch, and has a higher porosity, which makes it suitable for coloring. The increase in wear resistance is only moderate, unlike Type 3, which is typically called hard anodizing. Again, the active agent is sulfuric acid, and the process as a whole is very similar to Type 2 anodizing, but there are 2 big differences. 1. The bath is kept at refrigerated temperatures, while Type 2 anodizing is performed at room temperature. And 2, the electrical current used in the process is about 2 to 3 times higher. This results in a much thicker oxide layer, about 0.002 of an inch, which has a hardness of 60 to 65 Rockwell C. That's in the same range as hardened tool steel. I'm going to perform Type 2 anodizing on the air bearing, because I'm looking for a decorative appearance and a modest increase in wear resistance. Now, I love anodizing. It's a deeply satisfying process, especially because it's surprisingly cheap and easy to do. But there are many safety and environmental hazards associated with anodizing, so I have to make this disclaimer. Do not attempt to anodize your own parts unless you are trained to properly store, handle, and dispose of strong acids and alkalis, and to protect yourself from the possibility of shock from exposed electrical circuits. A few thoughts on personal protection. During the anodizing process itself, the required personal protective equipment is pretty minimal. Safety glasses and disposable gloves are fine. But when directly handling or mixing corrosive chemicals, the PPE requirements are greater. A face shield, a coat to cover the entire body, sturdy work boots, and forearm covering acid-resistant gloves made of latex, PVC, or nitrile rubber. Another issue is corrosive fumes and mist, especially those generated by the anodizing process. Wearing a respirator is a basic precaution, but there's really no substitution for proper ventilation. This is doubly true because the fumes and mist are harmful not only to human tissue, but also to any metal surfaces in the area. So I'm going to be performing the anodizing process under a localized exhaust hood. Type 2 anodizing consists of 4 basic steps. 1. Clean. 2. Anodize. 3. Dye. And 4. Seal. The first step in any anodizing process is thorough cleaning of the aluminum surfaces to remove any contaminants which will inhibit the formation of the oxide layer. A chemically dirty part may anodize incompletely or inconsistently, resulting in poor color take-up and a blotchy, uneven appearance. In order to determine the real effect of cleanliness on the final quality of anodized surfaces, I performed an experiment by exposing some test samples to a number of different contaminants and then anodizing them. I used color uniformity as a simple indicator of the quality of the final anodized surface. The first sample I handled with unwashed bare hands. Here it is on the right after anodizing. On the left is a control sample which was cleaned properly and handled with gloved hands. Handling with bare hands appears to have had little or no effect. The second sample I sprayed with light oil. Here it is after anodizing. Again, this contaminant did not seem to have much of an effect. The results from these first 2 tests are not completely conclusive, but they indicate that the electrochemical reactions which take place in the anodizing tank can strip loose dirt and light oils off a part surface. On the third sample, I applied some heavy cutting oil. This resulted in poor color take-up right around the edges, which in general are susceptible to incomplete anodizing. To the fourth sample, I applied some adhesives, heavy-duty tape residue, and superglue. These contaminants had a very noticeable effect on color uniformity. The fifth sample was just the end of the bar stock I used to machine the air-bearing body. It had a raw extruded finish on the cylindrical surface, and permanent marker and spray paint on the end. The extruded surface fared surprisingly well, but the marker and paint acted like a mask to prevent those areas from being properly anodized. 2 contaminants I did not test were buffing polishing compounds and heavy surface oxides, but these contaminants are well known for their adverse effects on anodized surface quality. I was surprised to see that the anodizing process was relatively tolerant of mild contamination at the initial cleaning step, and I wondered if this was also true for the other steps in the process. So I performed another test in which I handled some samples with bare hands at various points in the process. Here are the results. Going from left to right, first is the control sample, which was minimally handled with gloved hands throughout the process. Second is a sample which was improperly handled only before anodizing. Third is a sample which was improperly handled only before dyeing, and fourth is a sample which was improperly handled only before sealing. These results are not completely conclusive, but they indicate that mild surface contamination at the beginning of the anodizing process has less negative impact on the final quality of an anodized surface than using poor lab practices and not maintaining cleanliness
throughout the rest of the process. So I'm going to make a best effort at initial cleaning, wear gloves, and minimally handle the part throughout the process. To clean, I use a 50-50 mixture of distilled water and concentrated crystal simple green, an uncolored, unscented version of the well-known household degreaser. A good scrubbing usually does the trick, but a few minutes in an ultrasonic cleaner is even better. This is just a cheap consumer-grade model intended for cleaning jewelry, but it works pretty well on small parts. I add the water and degreaser, put the part in a basket, put the basket in the cleaner tank, and set it for 480 seconds, or 8 minutes. The ultrasonic cleaner agitates the cleaning solution with high-frequency sound waves, creating microscopic bubbles which violently implode on the part surface and mechanically remove contaminants. After the time is up, I remove the part and rinse it in distilled water. I use a wash bottle to get any lingering cleaning chemicals off the surfaces. How clean is clean enough? There's a simple, commonly used test for surface contamination called the water break test. Essentially, this test compares the relative strengths of water's surface tension, that is, the attraction of water molecules to themselves, and the part surface's hydrophilia, that is, the attraction of water molecules to the surface. If a contaminated surface is wetted with distilled water, the water will be more attracted to itself than to the surface, so it will form beads or blotchy areas. But if the surface is clean, then the water will be attracted to the surface enough to form a uniform film. This part appears to be clean. Passing the water break test is considered a minimum requirement for a part to be ready for anodizing, but it's not a guarantee of cleanliness, because the water break test is prone to giving false negatives. Cleaning solutions commonly contain surfactants, additives which lower surface tension. Even a relatively small quantity can cause a contaminated surface to pass the water break test. There are other tests. For example, the acid copper test is performed by dunking the aluminum part in a solution of water, copper chloride, and hydrochloric acid. If the part is free of contaminants, then chemical activity at the surface will pull copper out of the solution and deposit it in a film on the surface. This test is sensitive to contaminants like adhesive films, paint, and surface oxides, which the water break test might not pick up. And I think it's a pretty neat trick of science magic. After cleaning, professional metal finishers will often perform some kind of pre-treatment to remove surface imperfections and achieve a particular finish. One such treatment is to etch the aluminum in a room temperature solution of 3 to 5% sodium hydroxide, also known as lye or caustic soda. The etching process results in a uniform matte finish. It also tends to reveal alloying elements present in the aluminum, like iron, silicon, copper, which are not soluble in sodium hydroxide. This leaves a grayish-blackish residue called smut on the surface. Some of this can be wiped off, and sometimes the acid in the anodizing solution is enough to remove it. But the professionals will typically add another step and desmut the aluminum in a solution of 10 to 20% nitric acid. This stuff is very effective at desmutting the part surface. If a bright finish instead of a matte finish is desired, then an alternative pretreatment is electropolishing. The electropolishing process is similar to the anodizing process, but you crank the knob up to 11. A high-viscosity electrolyte solution, typically containing phosphoric acid, is heated up to around 180 degrees Fahrenheit. The part is submerged in the solution, and a relatively large electrical current is passed through it. As the material begins to dissolve, the peaks or high points of the rough surface are attacked more rapidly than the valleys or low points. This results in a fine surface finish, even in areas which are hard to reach with mechanical buffing and polishing processes. Pretreatment is largely a matter of personal aesthetic taste. Since it's not absolutely necessary, and since it adds more complexity and yet more nasty chemicals to the process, I usually skip these steps altogether.
Okay, once the part is clean, the next step is anodizing. The minimum equipment requirements for the anodizing setup are a corrosion-resistant tank, an acid-based electrolyte solution, a direct current electrical power source, and 2 electrodes. One negatively charged cathode, which is just a piece of sheet metal, and one positively charged anode, which is just the part.
First is the tank. I'm going to use a plastic bucket. Most plastic buckets are made of HDPE, or high-density polyethylene plastic. HDPE has excellent chemical resistance to sulfuric acid, so this is a good choice. A quick way to verify the construction material is to look at the number inside the triangular chasing arrows symbol on the bottom of the bucket. A 2 means HDPE. Next is the electrolyte solution. When an electrolyte like a salt, acid, or alkali is dissolved in water, it separates into positively and negatively charged atoms or molecules called ions. This solution can conduct electricity through the movement of these ions. For the electrolyte, I'm going to use battery acid, which is easily sourced at auto parts stores. Battery acid contains about 30% sulfuric acid, which is a little too concentrated. I dilute it with an equal part by volume of distilled water to get the concentration down to about 15%. I always add acid to water, never water to acid, in order to avoid a violent exothermic or heat-generating reaction. Next is the direct current power source. I've heard of people using car batteries and battery chargers, but anodizing is best accomplished with a power source capable of maintaining a stable, constant current. I use a dedicated bench power supply. This little model is capable of both constant voltage, 0 to 30 volts, and constant current, 0 to 10 amps settings. Finally, the electrodes. This process is called anodizing because the aluminum part becomes the anode, or positively charged electrode, in the electrolytic cell. I use a titanium welding rod to electrically connect the part and suspend it in the anodizing tank. Aluminum rod could also be used, but it's not as ideal because the rod will anodize along with the part and lose its conductivity. I fold one end of the rod back onto itself with pliers to get a snug fit in the threaded hole, and then I bend the rod back 90 degrees. The rod needs to make good electrical contact with the part, but it should also be placed in an inconspicuous location because the part will not be anodized at the point of contact. I use a wooden dowel as an insulating rack from which to hang the part. I fully submerge the part in the anodizing solution, then I bend the top of the rod to hook it onto the dowel, and I snip off the excess rod with wire cutters. The cathode, or negatively charged electrode, is a piece of lead sheet. Lead lasts longer in the anodizing solution than the other common cathode material, 6063 T6 aluminum alloy. But the trade-off is dealing with lead in the waste stream. The recommended ratio of anode to cathode surface area is 3:1, but this is not supercritical, and in any case, it's hard to maintain. Time to set the power supply. The required electrical power is based on a recommended ratio of electrical current to surface area of the aluminum part, called current density, and expressed in amps per square foot. The commonly recommended current density for commercial Type 2 anodizing processes is 12 amps per square foot. However, current densities as low as 3 to 6 amps per square foot can be used to achieve a similar result with longer anodizing times. Some people actually prefer using a lower current density because it saves on equipment costs and it results in a more open pore structure which takes color better, but at the expense of a little wear resistance. Here are two test samples I anodized at different current densities. The sample on the left was anodized at 12 amps per square foot for 30 minutes, and the sample on the right was anodized at 6 amps per square foot for 60 minutes. The sample on the right took up noticeably more color, but I'm going to use the recommended current density of 12 amps per square foot. Let's do the math. According to my solid modeling software, the aluminum body has a surface area of 0.04 square feet. So, the current should be 0.04 square feet times 12 amps per square foot equals 0.48 amps. The way to set a constant current on this particular power supply is a little odd. With the amperage and voltage knobs at their minimum settings, the positive and negative leads are shorted together. The power supply is turned on, the voltage knobs are set to the middle of their range, and the amperage knobs are adjusted to the desired setting. I turn the voltage knobs back to their minimum setting. I attach the alligator clip on the positive lead of the power supply to the titanium rod. I attach the alligator clip on the negative lead of the power supply to the lead sheet. I slowly turn the voltage knobs back up to their maximum. The power supply will vary the voltage to maintain the desired current setting. I mentioned earlier that aluminum oxide is an electrical insulator. As the oxide layer on the aluminum grows, the part will become more resistive to the flow of electrical current. So, the power supply will have to gradually increase the voltage to maintain the desired current setting. Anodizing has begun. When electrical current is flowing through the electrolyte solution, some of the sulfuric acid decomposes into positively charged hydrogen ions and various negatively charged ions. The hydrogen ions are attracted to the negatively charged lead cathode, where they form hydrogen gas bubbles. The negatively charged ions, including oxide, hydroxide, and sulfate, are attracted to the positively charged aluminum anode, where they react with aluminum on the surface to form aluminum oxide. Simultaneously, the remaining acid in the solution dissolves the aluminum oxide. This continuous formation and dissolution of the oxide layer creates a sort of tunneling effect, which is responsible for the oxide layer's porous structure. There are a couple of items which can be added to this minimum anodizing setup to improve the consistency of the process. The first is some form of agitation. This will ensure that everything in the solution, water, sulfuric acid, and dissolved aluminum, stays in suspension, and that the part will always have contact with fresh solution. Is this absolutely necessary? Well, the sample on the left was agitated, and the sample on the right was not. I don't see a difference between them, but this is a very small, very simple part without any internal features. For the best process consistency, it's good to use agitation. This can be achieved by pumping, like with this submersible aquarium pump, or by aeration, like with this sintered stainless steel stone commonly used by homebrewers. This is my method of choice. I attach some PVC tubing to the stone, clip it onto the side of the anodizing tank, and run filtered compressed air through it. The other improvement to the setup is some method by which to monitor the temperature of the solution, like this aquarium thermometer. Type 2 anodizing is typically accomplished at room temperature, officially set at 68 degrees Fahrenheit, which may or may not be the actual ambient temperature in a given area. Also, resistance in the electrical circuit causes continuous heating of the solution, which may or may not be adequately dissipated to the environment. If needed, temperature regulation can be accomplished with lower current densities, larger volumes of electrolyte solution, or special control equipment. But the temperature in the tank is pretty ideal in this case. How long should the part remain in the anodizing tank? The total anodizing time required can be estimated with something called the 720 rule. This guideline states that 720 amp-minutes per square foot are required to produce an oxide layer with a thickness of 1/1000th of an inch. So, 720 amp-minutes per square foot divided by 12 amps per square foot equals 60 minutes to achieve an oxide layer with a thickness of 1/1000th of an inch. However, I'm going to shoot for 1/2 of an inch and anodize the aluminum body for only 30 minutes. This will save a little time and energy and still result in good colorability. Once anodizing is complete, the power supply is turned off, the lead is unclipped, and the part is removed from the solution. It's important not to carry over any acid from the anodizing tank to the dyeing tank. A quick rinse with distilled water is usually sufficient, but a quick dip in a solution of distilled water and sodium bicarbonate or baking soda is even better because it helps neutralize any remaining acid. The sample on the left was rinsed and dipped in the manner just described, and the sample on the right was placed directly into the dyeing tank. As you can see, the sample on the right has splotches of uncolored area on its top surface, and large swaths of uncolored area on its side surface, where the acid got trapped between the surface and the titanium rod wrapped around it. Alright, the next step is dyeing. I use inexpensive fabric dye for this. Professional quality anodizing dyes are also available from online suppliers, and unlike fabric dyes, which are usually organic, these anodizing dyes are usually synthetic, so they won't fade over time because of exposure to ultraviolet light. But I've always had very good results with fabric dye. I use a ratio of 50 milliliters of dye per 1 liter of distilled water. The temperature of the dye solution is maintained between 120 and 140 degrees Fahrenheit with a hot plate in order to improve color take-up. I place the part into the dyeing tank. If the part was anodized properly, it will begin to take color almost immediately. This looks promising. Parts are typically left in the dyeing tank for 1 to 15 minutes, depending on the desired color depth. During this time, the dye penetrates into the pores of the oxide layer. Here's what the part looks like after 1 minute, 5 minutes, 10 minutes, and 15 minutes. As you can see, most of the coloring occurs in the first minute. I remove the part from the dyeing tank after 15 minutes. At this point, the part is a little darker than I want for the final color. This is purposeful, and the reason will become clear in a moment. Once the part is finished dyeing, the next and final step is sealing. This is typically accomplished in pure distilled water. To minimize sealing time, the temperature should be between 200 and 212 degrees Fahrenheit, around the boiling point of water. I place the part into the sealing tank. You can see there was a little residual dye on the part. The part only needs to be left in the sealing tank for 10 to 15 minutes, but I leave it in for 30 minutes just to be safe. During this time, some of the aluminum oxide in the anodized outer layer of the part reacts with the water and is converted to the mineral boehmite, an aluminum monohydrate. Because this substance has a greater volume than aluminum oxide, as it grows, the pores in the anodized layer are closed off. This effectively seals the interior of the part, permanently retaining the dye and improving the part's corrosion resistance. Sometimes additives are used in the sealing solution. For example, nickel acetate is sometimes added because the nickel ions help fill in the pores in the anodized layer. Anyway, when the part is done sealing, I remove it from the tank. You can see that a little bit of color was lost. Once the part is cool, it's done, and I'm very happy with the way it turned out. The color is rich and uniform, inside and out. Nice.
There's just one more item we need to discuss: what to do with all this leftover acid. The obvious thing to do is just to leave it in the anodizing tank with a lid on it and use it the next time something needs to be anodized. The electrolyte solution will handle many anodizing cycles, but at some point it will contain too much dissolved aluminum and it will need to be replaced. This brings up the inevitable waste disposal problem.
As you can see from this pH paper, the sulfuric acid is really acidic. But it's not the sulfuric acid that's the problem. The acid can be easily neutralized with an alkali like baking soda. This effervescent reaction produces water and a salt, sodium sulfate, as byproducts. Once all the baking soda has bubbled away, and adding more doesn't result in more bubbling, then the acid is neutralized and the pH should be in the 6 to 8 range.
Many municipalities allow clean, neutralized acid to be disposed of in the sewer system. But processed liquids which contain metals like aluminum, or especially heavy metals like lead, are typically treated as hazardous wastes. Regulations vary, but local hazardous waste facilities can provide disposal instructions. So, the aluminum body is anodized and ready to be epoxied to the graphite insert. But that's enough for this video. Stay tuned for part 4, and as always, I hope you learned something.